power of 0, which is 1. Again, it's a constant, so we can take it out of the integral so that we have 3e minus 1, the integral of 0 between 0 and pi of sine z in dz, which gives us 3e minus 1 cosine z between 0 and pi, negative cosine z between 0 and pi, which gives us 1 minus minus 1, which is 2, from which 6e minus 1 Now, the next one, we have to express the integral negative 1 negative root of 1 minus x squared, root 1 minus x squared, x squared plus y, 2 minus x squared minus y. So we need to understand what region this represents. We have two paraboloids. Two paraboloids, one pointing upwards, which is this one here, x squared plus y squared, and one pointing downwards, which is 2 minus x squared minus y squared. So we are interested in this region between the two paraboloids. So let's perform the cylindrical substitution. Cylindrical substitution is x is equal to r cos theta, y is equal to r sine theta, and z is equal to z, and dx, dy, dz becomes r dz, dr, d theta. So with these substitutions, our integral becomes, let's leave the limits untouched for now and perform only a substitution so that we have r squared to the power of 3 over 2 times r dz, dr, d theta. Now we need to substitute the integration limits and express them in terms of the coordinates z, r, and theta. The first one is the integral with respect to z, but z stays the same. So we simply need to replace x squared plus y squared with r squared, and 2 minus x squared minus r squared with 2 minus r squared. Now we need to look at the coordinates for x and y. Looking at the limits of the integral in terms of the Cartesian coordinates, we see that we have a circle of radius 1. So these two identify the upper and lower portion of the circle along y, and -1 and 1 identifies the coordinates along x. So expressing a circle of radius 1 in terms of Cartesian, in terms of polar coordinates, means that r will vary between 0 and 1, and theta will vary between 0 and 2 pi. So now that we have expressed the limits of integration in terms of cylindrical coordinates, we can solve this integral, which is fairly straightforward, as 8/35 pi. The last example is to evaluate the integral -2 to 0 square root of 4 minus x squared, 0 square root of 4 minus x squared minus y squared of x squared plus y squared plus z squared dz dy dx. So we need to understand what we are integrating over. The first is dz. So the plane z equals 0 represents the lower limit, and the equation 4 minus x squared minus y squared represents the sphere. So we are integrating in this region here below the sphere of radius 2. So since we're using spheres, it is advisable to use spherical coordinates. Spherical coordinates, we know that x squared plus y squared plus z squared is equal to rho square, and dz dy dx becomes rho square sine phi d rho d phi d theta, and x is equal to rho cos theta sine phi, y is equal to rho sine theta sine phi, and z is equal to rho cos phi. So we need to represent that in terms of spherical coordinates. So let's leave the integrals without limits for now. So we have rho square, which is the x squared plus y squared plus z squared. And then we have rho square sine phi d rho d phi d theta, which corresponds to the dv. So the limit here will be between 0 and 4 minus rho square rho square times sine phi. And then we have to determine the limits for phi and theta. Phi identifies the elevation angle along this direction, which means we have to go all the way down to the z equals 0 plane, corresponding to 0 and pi over 2, while theta represents the azimuth, which will be between 0 and 2 pi . So again, a fairly straightforward integration that gives us 32 over 5 pi as the solution. Now we move on to matrices. Matrices are a set of real or complex numbers arranged in rows and columns. A matrix typically has m rows and n columns, and it is defined as an m by n matrix. So rows first, column second. Matrices are added, subtracted, simply by adding and subtracting the corresponding elements, while they can only be multiplied together if the number of columns in the first matrix is the same as the number of rows in the second matrix. When studying matrices, we look at the determinant, which is a special number typically associated with matrices that is useful in the solution of linear systems. So determinants can only be found for square matrices. Where matrix formulation becomes powerful and useful is in the solution of linear systems. Since we, instead of solving simultaneous equations, we can solve them by matrix methods. We know of 3 methods that allow us the solution of linear systems. The first one listed here is the determinant method. So we calculate the determinant of these systems of 4 equations, but we mentioned that determinants can only be solved for square matrices. So you will notice that each determinant here is from a 3 by 3 matrix that comes from the matrix of the solution of the linear equations with 1 row removed. So if we want to find x, we need to remove the first column of elements. When we want to find y, we remove the second row of elements. When we find z, we remove the third row of elements. And finally, when we want to find the determinants of the coefficients, we simply remove the last row. The second method that we know is by solving the inverse of the matrix. And remember that a matrix can only be inverted if its determinant is different from 0. If the determinant is equal to 0, the inverse does not exist and cannot be found. Finally, the last method that we know is that of Gauss-Jordan, which requires writing the augmented matrix and simplifying it to a triangular matrix from which we can then solve one by one the various variables. So let's look at how we can use the three methods to solve this system of equation. So the first method relies on, let's say, finding the determinant, finding the inverse, so that the solution of this system, which we can express as 1, 2, -3, 2, -1, -1, 3, 2, 1. This is our matrix A. And then we have x, y, z is equal to 3, 11, -5, which is our matrix B. So this is A, this is X, and this is B. So we can solve this by taking the inverse such that X is equal to the inverse of A times B. The inverse of the matrix A in this case is 1/30, which is the determinant. -1, 8, 5, 5, -10, 5, -7, -4, 5. And we need to multiply this by B. So we will have that x, y, z is equal to A to the inverse of A times B, which gives us 2, -4, -3 as the solution. Now let's look at the determinant method. For the determinant method, we have to rearrange the equation so that the matrix becomes 1, 2, -3, -3, 2, -1, -1, -11, 3, 2, 1, 5. From this augmented matrix, we need to calculate the determinants delta 0, delta 1, delta 2, and delta 3. So delta 0 comes from removing this column here. So delta 0 is the determinant of the matrix 1, 2, 3, 2, -1, 2, -3, -1, 1, which gives us -30. Then delta 1 comes from removing the first row of, the first column of the augmented matrix. So the determinant 2, -1, 2, -3, -1, 1, -3, 11, 5, which gives us 60. Then we have delta 2, which comes from removing the second column. So we'll have 1, 2, 3, -3, -1, 1, and -3, -11, 5. And this becomes 120. And finally, the last determinant, delta 3, comes from removing the third column. So we have the following matrix, and the determinant is -90. So the solution is given by x delta 1 is equal to -y delta 2, which is equal to z over delta 3, which is equal to -1 over delta 0. So this gives us x divided by -30 is equal to -y divided by 60, which is equal to z over -90, and this is equal to 1 over -30, from which x is equal to, so this is 60, this is 120, and this is 90, sorry. So x is equal to 2. X is equal to 2. Y is equal to -4, and Z is equal to -3, which corresponds to the solution we found earlier from the inverse method. Now, let's see how we can solve this as Gaussian elimination. So we need to build the augmented matrix. The augmented matrix is 1, 2, -3, 3, 2, -1, -1, 11, and 3, 2, 1, -5. So we need to subtract 2 over 1 times A1I from the first row, and subtract 3 over 1 A1I from the third row. So we multiply all elements of the first row by 2, and then we subtract them from the second row. So this gives us 0, -5, 5, 5. And then we multiply all the elements in the first row by 3. And then we subtract them from the third row, giving us 0, -4, 10, -14. Now we take -4 over -5 times all the elements, sorry, all the elements in the second row, and we subtract that from the third row, so that this gives us 1, 2, -3, 3, 0, -5, 5, 5, and 0, 0, 6, negative 18. Now we detach the augmented matrix so that our system becomes 1, 2, negative 3, 0, negative 5, 5, 0, 0, 6, x, y, z is equal to 3, 5, negative 18. So we have a system that is given by the equations x plus 2y minus 3z is equal to 3, negative 5y plus 5z is equal to 5, and 6z is equal to negative 18. So we work our way backwards from z. So z is equal to negative 3. We substitute it into the equation above to find that y is equal to negative 4. And then we substitute both into the first equation to find that z is equal to 2. Unsurprisingly, we find again the same values for x, y, z that had been found through the determinant method and the inverse method. So in many engineering applications, we have, particularly those involving oscillations, we have equations that can be expressed in the form of ax is equal to lambda y. This value, this parameter lambda, is typically known as the eigenvalue or characteristic value of the matrix A. And the values of these latent roots are found by solving the determinant of A minus lambda I matrix. The corresponding solutions of the system equation are known as eigenvectors. So each eigenvalue will identify a set of eigenvectors. So let's look at how we find the eigenvalues and the corresponding eigenvectors for this matrix A. So we have our matrix A, which is 2, 0, 1, negative 1, 4, negative 1, negative 1, 2, 0. So to find the eigenvalues, we need to find the solution to determinant of A minus lambda I. So the matrix A minus lambda I is 2 minus lambda, 0 minus 1. Sorry, 1. Negative 1, 4 minus lambda, negative 1, negative 1, 2, negative lambda. So we take the determinant of this matrix so that the determinant becomes 2 minus lambda times lambda square minus 4y plus 3 equal to 0. giving us the 3 eigenvalues 2, 1, and 3. So each of these eigenvalues will be associated with or will identify an eigenvector. So to find the eigenvectors, we want to solve the equation A minus lambda I x is equal to 0. So when lambda is equal to 2, we have lambda A minus lambda I will be 2 minus 2, 0, 1, negative 1, 4 minus 2, negative 1, negative 1, 2, negative 2, times x, y, z, equal to 0, 0, 0, corresponding to z equals to 0, negative x plus 2y minus z is equal to 0, and negative x plus 2y minus 2z is equal to 0. So the first eigenvector is x one half x 0. So any set of values x that satisfy this requirements, these constraints, identifies an eigenvector for the eigenvalue x lambda equals 2. So you could have an eigenvector 1, 1 half 0, or you could have an eigenvector 2, 1, 0, or you could have an eigenvector negative 3, negative 3 over 2, 0. So any of these eigenvectors represents a solution for what lambda equals 2. Then we look at the next eigenvalue, which is 1. So when y is equal to 1, when lambda is equal to 1, the equation becomes x plus z is equal to 0, negative x plus 3y minus z is equal to 0, and minus x plus 2y minus z is equal to 0. So this gives us the set x is equal to negative z, y is equal to 0, and x is equal to negative z. So any pairing, any set that satisfies these constraints will be an eigenvector for the eigenvalue lambda equals to 1. Sorry, there's a question, how do we know to solve for x, y, or z? This is an equation of 3 variables, 3 unknowns. So you simply solve it as you would normally. So this eigenvector is x, 0, negative x. So we can have 1, 0, negative 1, negative 1, 0, positive 1, and so on. So Donovan, do you understand that it's a system of equation in 3 unknowns? You have 3 equations in 3 unknowns. So you solve, and some values you may get 0. Others you may get expressed in terms of one of the other variables. So earlier, now we find that y is equal to 0. Earlier, we saw that z was equal to 0. And when we do lambda equal to 3, the system of equation becomes negative x plus z is equal to 0. Negative x plus y minus z is equal to 0. And negative x plus 2y minus 3z is equal to 0. So this is solved as x is equal to z, y is equal to 2z, and x is equal to z. So this gives us a possible eigenvector of x to x corresponding to, for example, 1 to 1 or negative 1/2, negative 1, negative 1/2. Again, both eigenvectors are solutions for the eigenvalue lambda equals to 3. Any questions on this? Well, then let's go back to PowerPoint. So vector fields are multidimensional regions into which we can identify vector valued functions. So value functions that not only have a magnitude, but also have a direction. Typically, when looking at vector fields, we can identify a particular mathematical operator, which is known as the gradient, which we have already seen when looking at multivariable functions. Moreover, when looking at vector fields, we may be able to identify a particular type of function, which is known as a potential function. So the potential function is the derivative of, is the gradient of the vector field. If this happens, then the vector field is subject to some interesting properties linked to the vector field being conservative. The most interesting conclusion or property of a conservative vector field is that it is independent of the path taken. So going from point A to point B across that vector field is going to take the same amount of, let's call it work or energy, no matter what path is taken. So taking a straight line or going for a long diversion will not change the overall work done to go from point A to point B. Further, as a consequence, it follows that a path that starts and finishes at the same point will always have a work of 0. So let's see how we can find if a vector field is conservative or not. We've mentioned that to find if a vector field is conservative, we need to identify a potential function for that vector field. So if we have a vector field defined by 2xy minus 3 and x squared plus cos y, we need to identify a potential function for which the partial derivative with respect to x is 2xy minus 3, and partial derivative with respect to y is x squared plus cos y. So if this is our derivative of the potential field, we have that 2xy minus 3 in dx is solved as x squared y minus 3x plus an integration constant or an integration function gy. Now let's take the partial derivative of this with respect to y, which will have to be 2xy minus 3 times 0 plus g prime y. And this has to be equal, sorry, the first term is incorrect. This is x squared. And this has to be equal to x squared plus cos y, which is this term here. So the x squared cancels out, and we find that g prime is equal to cosine y. Integrating this gives us that g of y is sine y plus c. So we bring all this together to find that the potential function f is x squared y minus 3x plus sine y plus c. Just to confirm, let's take the partial derivative of this potential function with respect to x, which gives us 2xy minus 3. And the partial derivative with respect to y is x squared plus cosine y. So we can see that these two partial derivatives are indeed the components of the vector field. So we have managed to identify a potential field, a potential function, and hence the vector field f will be conservative. Now the second one is a vector field 3x squared y squared minus 2y, x squared y minus 2x. So this means that the function, the potential function, has to have partial derivative with respect to x as 3x squared y squared minus 2y, and partial derivative with respect to y as x squared minus 2x. So let's take the integral of 3x squared y minus 2y in dx to give us x cubed y minus 2xy plus gy. And now let's take gy. So we have to make sure that df dy, which is equal to x cubed minus 2x plus g prime y, is equal to x squared minus 2x. Notice the 2x cancels out, but g prime y is equal to x squared minus x cubed, which is clearly impossible. So this is not a conservative vector field. Do you have a class coming up? Yes, no, I mean at 12. Yeah, okay. Ryan, we can say no, we cannot say that it is not conservative until we determine that we cannot find a potential function. Since we cannot find a potential function, it means that the vector field is not conservative. So since in the previous worked example, we cannot find a potential function because g is a function of x when it should only be a function of y, it means that there is no potential function, the partial derivatives of which are the components of the vector field. Okay. Right. I think we'll finish here. So Thursday, I will be available as usual for the tutorials. If you have any clarifications or doubts, just turn up for the tutorials.